When you collect raw data for a study, you aren't handed clean answers. You get thousands of individual data points, a chaotic wall of numbers that is completely unreadable to the naked eye. Naturally, our brains try to find patterns in that chaos, but relying on raw human intuition to judge whether a pattern is actually real is a mathematically dangerous game. Say you test two teaching methods. Group A scores 81, Group B scores 84. You automatically assume B is better. But is that difference a breakthrough or a random fluke in a small sample? When we look at variance, that gap vanishes. Data analysis is the strict mathematical system we use to strip away that subjective human bias. It cleans the chaos and allows us to confidently separate statistical noise from objective truth. Before any complex math can even begin, researchers have to define exactly what type of data they possess. This single classification dictates every decision that follows. We start with categorical measurements. Nominal data gives us distinct labels, like nationality or gender, while ordinal data gives us ranked scales, like strongly agree to strongly disagree. We contrast those with interval and ratio data. These represent true continuous numbers, things like precise test scores, exact temperatures, or literal word counts. Once the data is categorized, researchers use descriptive statistics to summarize the exact shape and spread of their specific sample. We find the center of our data using the mean, median, or mode. Then we measure how far the rest of the numbers scatter away from that center using the standard deviation. But there is a catch. Descriptive statistics perfectly paint a picture of the immediate sample in front of you. On their own, they are entirely useless for proving if those findings apply to the broader population. To make confident claims about the real world beyond the immediate sample, we have to move into inferential statistics. Think of this as a scientific trial. We start with the null hypothesis. This is the default assumption that your intervention did absolutely nothing and no real difference exists. The researcher's objective is to put their data on trial and disprove that default state. They want to support the alternative hypothesis, proving their work actually created a true, measurable effect. The ultimate judge in this trial is the p-value. It calculates the exact probability that your observed results happened by pure dumb luck. In applied linguistics, the standard threshold is a p-value of less than 0.05. This means there is less than a 5% chance your results are a random fluke. Cross that line and the null hypothesis shatters. Hypothesis testing provides a ruthless mathematical threshold to declare a discovery valid. It prevents scientists from publishing a lucky draw as a concrete fact. Selecting the correct statistical test to cross that threshold depends entirely on your specific research question and the number of groups you are comparing. If you are looking at exactly two groups, you use the t-test family. An independent samples t-test compares two separate groups, while a paired samples t-test compares the same group measured before and after an intervention. But if you have 3 or more independent groups, like testing 3 different teaching methods, you strictly require an analysis of variance, or ANOVA. This allows you to compare all the groups simultaneously without artificially inflating your error rate. If your focus shifts to testing relationships rather than comparing groups, the tree branches again. We use correlation to see if 2 variables move together, and simple linear regression to determine if one variable significantly predicts the outcome of another. Choosing the wrong branch of this decision tree mathematically invalidates your entire study. Building this logical map is the single most critical phase of quantitative research design. There is a dangerous misconception in research. Achieving statistical significance proves a difference is mathematically real, but it does not prove that difference actually matters. For that, we need effect size. This is the vital companion metric that measures the actual magnitude and real-world impact of the difference you discovered. A result can be statistically significant, but practically invisible without a strong effect size. Once a meaningful discovery is made and measured, it must be reported in a universally understood format, or the scientific community simply cannot replicate it. This is where APA 7th edition formatting comes in. It standardizes how we report these complex statistical symbols, ensuring exact means, p-values, and effect sizes are communicated without ambiguity. Which brings us back to that overwhelming cloud of raw data. By systematically defining our variables, applying the correct inferential tests, and standardizing our reporting,
We possess the framework to tame the chaos. Statistical analysis is the universal language we use to discard falsehoods, prove what works, and confidently map the reality of our world.